Hello and welcome to Chapter 10 for AP Chemistry, Liquids and Solids. I am your gracious host, Grandmaster C. Alright, so liquids and solids, if we look at them compared to gases, there's some comparisons we can make, whether they're compressible or incompressible. Density won't change with temperature in liquids and solids, but in gases it actually does. You can think about how gas particles, they will expand more with a higher temperature because there's more energy and the gases are hyper! Okay, so that's the way it goes. Now, how come we're seeing similarities between solids and liquids? Okay, well, if you think about it, molecules are close together in solids and liquids, whereas in gases they are farther apart. Yeah. That would make some things. Now, of course, what holds them together are intermolecular forces, and that would be a pretty important idea. We talk about inside molecules. We have intramolecular, where the atoms are bonded to each other. Those would be intramolecular forces. So when we look at intermolecular forces, we are talking about the forces between the molecules themselves. Okay? Now, these are what hold the molecules together in the condensed states. So intermolecular forces, we've got strong intermolecular forces like covalent bonding and ionic bonding. Then we look at the weak intermolecular forces where we have dipole-dipole and London dispersion forces. Okay, dipole, where have you heard that before? Ah, yes, polarity! Polarity, you know, the positive and the negative, the cation and the negative. Now, cation, do they have something to do with the dipole? Yeah, it actually does. Okay, but anyway, so of course, when you have phase changes, like going from solid to a liquid, liquid to a gas to a liquid, okay, the molecules pretty much stay intact. And energy, we can use energy to overcome these forces. Well, if you stop and think about it, if you want to create steam from liquid water, what do? We add energy to it! Yes, can you imagine that? Oh. So, what's up with dipole-dipole? Well, remember, polar molecules can attract each other. Well, how come? That has to do with the positive and the negative, because Paula Abdul told us. Opposites attract. Okay? So polar molecules will attract each other. Now, here's the thing, though. With polar molecules, what can we say about higher boiling points? They have higher boiling points, usually, than nonpolar molecules of roughly the same molecular mass. Why? Well, it's going to take more energy to overcome the polarity. Okay, that positive minus thing, whereas when we look at nonpolar, where electrons are shared equally, and life is beautiful, and we can have those anime characters with the big eyes and small mouth, okay, it doesn't work that way. So higher boiling points for polar molecules, generally speaking, than nonpolar molecules. Okay? So why the higher boiling points? Yeah, TJ, why are we having the higher boiling points? Well, let's look at the dipole-dipole here. Okay? So here we have our SO2 molecules. Okay? There's dipole-dipole and London forces in there. This also accounts for the higher boiling points. Okay, so an example of a polar molecule is SO2. Now you'd say, hey, why would that in fact be polar? Well, if you look, you have electronegativity with the sulfur and the oxygen. Which direction is this polarity going to be happening? Where's the most electronegative one? Which is the most electronegative? Is it going to be the sulfur or the oxygen? Tough one, but you'll get the idea. All right, continuing with dipole-dipole. So molecules, they'll line up in the presence of an electric field. The opposite ends of the dipole, think positive, negative, can attract each other, so the molecules kind of stay together. Am I making you dizzy, boys and girls? I get to do that. This is, my time. All right. So it is, however, these dipole-dipole, they're only 1% as strong as the covalent bond. So they're kind of weak, but you can't just simply say, it doesn't do anything. It does. There definitely is an effect. Now, of course, the further apart that these molecules would be, that have these opposite polar ends, then what happens is that dipole-dipole attraction is going to get weaker the further apart. Okay, that's just the way it is. It's true with a lot of things in life. Now, the thing is, dipole-dipole also play a small role in gases as well. Not going to worry about it. Hydrogen bonding. Odell, this one's for you. Oh, you hated hydrogen bonding, but we're getting into it, aren't we? Yes, we are, aren't we? Okay, it is the strongest type of intermolecular force that we have. Wait, is it stronger than dipole-dipole? Yeah, pretty much. Okay, now, here's the thing. You have an unusually strong dipole-dipole forces when the hydrogen is in fact attached to F, O, or N, the FON, if you will. So you can have HF, HO, HN, or you might sit there and think of OH, think of the hydroxide ion. You can think of NH3, for example, ammonia, NH4, ammonium, okay? So why particularly the F, the O, or the N? That's because the F, the O, and the N have high electronegativity. Now, fluorine has the highest, and number 2 would be, in fact, the oxygen. Okay, and then followed by the nitrogen. That's that high electronegativity. How badly does it want that electron that's shared with the other atom? Now, when you look at hydrogen, hydrogen's not, it's kind of wimpy, weak, okay, kind of like the Aquinas soccer team at last night's game, weak, okay. So, yeah, but they're also small enough to get close. That's the thing about hydrogen. Remember, hydrogen's small. So they're small enough to get close. And what does that do? It increases the boiling point. Okay? So that's a really important idea when we look at hydrogen bonding. But remember, hydrogen bonding is also used in water. This would explain things. Why does water have a higher boiling point? Okay? Why does water have certain properties, like water tends to stick together? It's, again, that hydrogen bonding that's in there, okay? And like I said, that's an AP Bio. Like I said, this one's for you, Odell, okay? But it increases the boiling point as well. Why would it increase the boiling point? Well, remember, if you've got another type of bonding that's there, it's going to require energy to overcome the bonding. So that's why we would see an increase in the boiling point. So let's check out these boiling points right here. Okay, so we can look here, the boiling point in degrees Celsius from negative 200 to 0. Oh, that's cold, man. To 100, hot, hot, hot. So if we look at these, you kind of notice as you go across the period, okay, you got it going down quite a bit, where water and HF and NH3, they're fairly respectably high in their boiling points. You notice how CH4, which is not a polar molecule, look how low of a boiling point it is. Wow. Just wow. But when you start looking at some of these, you notice that it's a lower boiling point. But as you go across the table, then what you start seeing is you see an increase in the boiling points. So it's just giving you guys an idea. You're not supposed to memorize this chart unless you are AP 5.1 and Dylan Attridge. Those two, yeah, they do. Hydrogen bonding in water. Oh my goodness. Well, you know, you may notice that the the molecule here is a little bit off. It really should be shifted down here, so the oxygen is where our delta negative is, and the hydrogens should be where our delta positives are. Okay, hydrogen bonding in water. Odell Part 2. So what does it allow the water to actually do? Well, it allows the water to make connections with each other, as you can see up here. Okay, so this is how the water would make hydrogen connections, hydrogen bonding. Okay, now remember, the hydrogen's not sticking to the oxygen, but there's certainly an attraction that is there. It's weak, but it is a critically important thing that we have. This allows water to do a lot of things. Okay. London dispersion forces. This is another thing. We're moving away from hydrogen bonding for a moment. We're going on into London dispersion forces, also known as van der Waals forces. That would be another thing here. So nonpolar molecules can also put forces on each other. They can. It's just not the same as a polar molecule, because polar molecule, you have your positive, you have your negative, and boom, that's what it is. But this would also, nonpolar molecules, they do put the forces on each other. Otherwise, you're not going to have solids, you're not going to have liquids. Think oil. Oil is nonpolar, okay? And as you know, oil would be kind of an important thing in our world because we depend on it for like plastics and gasoline and all those other wonderful things. Now electrons, now here's the interesting thing about nonpolar molecules. We think about electrons being shared equally, but electrons are not evenly distributed at every instant in time. Crisis! Okay. Oh my gosh. Oh, wait. Getting the camera back up here. Okay. Now, they have an instantaneous dipole. Wait, instantaneous? Yeah, that means at that moment, bam, you got a dipole right there. Okay? Now, it induces, it means that the atom that next to it is also going to create a dipole in response to that instantaneous dipole. Bam! Right, Evan? And Alan? And Cosmo? Yeah, absolutely. Okay. So what you're getting is an induced dipole interaction. This is dealing with the London dispersion forces, also known as van der Waals forces. Now, it's also abbreviated LDF. But you should be able to understand that. That would be for a nonpolar molecule, okay? So here's an example where we have got a couple of hydrogen atoms, molecules I should say. So here we go. Here's our hydrogen there, plus plus. Not a big surprise. And what happens here? You get a you get a minus. Oops, sorry. Hey, whoop. Hey. All right. Here's the idea. If you have plus plus here, and then you have a plus minus over here, oops, they're weak and short-lived. Okay, this is a really it didn't turn out quite the way that I wanted. But the idea is this. If you got a plus here, all right, and a minus here, let's say, and you have a plus here and a minus here, imagine that it would flip. One of the atoms would flip its dipole. Okay, so now where it was positive, it's now negative. And where it was negative, now it's positive. And what happens is, with that these will be attracted to each other. That's the general idea. Okay? Now, they're weak and short-lived, and these forces last longer at low temperature. That would make sense. Okay, eventually long enough to make liquids, and as I'm rapidly putting it on, we're going to stop here, ladies and gentlemen. With that, write the number 42 on your paper.